Imagine a rigid circular hoop of radius, A rotating at a constant angular speed omega, about its vertical diameter. On this hoop, a small, smooth ring of mass m is free to slide without friction. We specify the ring's position using the angle theta, measured from the lowest point of the hoop. As the hoop spins, the bead stays in contact, but where will it find its balance? First, let's analyse the forces in an inertial frame. Here, we only see real forces, gravity acting downwards and the normal force from the hoop pushing towards the centre. Now, let's switch to a frame co-rotating with the hoop. In this non-inertial frame, we must include the centrifugal pseudo force, which acts horizontally outward from the axis of rotation. To find the equilibrium positions, we look at the force balance along the tangent to the hoop. In this direction, the friction is zero, so the net force must be zero for the bead to stay still. Equating these tangential components, we get m times omega squared times a sine theta. Factoring out m and sine theta, we discover two possible conditions for equilibrium. Either sine theta is zero, or cosine theta equals g, divided by omega squared times a. The first solution, sine theta equals zero, points to the bottom of the hoop. At low speeds, gravity dominates, and the bead is pulled back to this point if disturbed. However, if the hoop rotates faster than a critical speed, the bottom becomes unstable. A new equilibrium emerges where the centrifugal force and gravity perfectly balance at a non-zero angle. Qualitatively, if you nudge the bead from this new position, the tangential force acts as a restorer, pushing it back toward theta naught. This makes the side position a stable equilibrium. So, the bead's behaviour changes at the critical frequency. Below it, the bottom is the only stable spot. Above it, the bead rises to a new, stable height on the spinning hoop.